Hello everyone. We have started or to some extent have finished the discussion associated with sensor parameters. We have seen that there are multiple parameters associated with sensors that are really very important as far as the sensor design or implementation is concerned. It's not only for the design but also for implementation purposes. You need to know different parameters that are important. For example, say sensitivity, range, and stuff like that. And we also have seen some details associated with sensor. For example, say calibration curve, which is very important as far as the sensor response is concerned, because most of the parameters that we have discussed can be calculated or measured from the calibration curve itself. If you buy a commercial sensor, you may find that in the data sheet the sensor manufacturer will provide you a calibration curve and may not explicitly mention many of the parameters that I have discussed. But from the data sheet or from the calibration curve itself, you will be able to extract that information. So in order to do this analysis, or in order to give you an understanding, in this particular lecture, I'll solve some of the problems associated with the same, so that you get a better understanding about the calibration curve, the parameters associated with sensors, and overall the sensor implementation and etc. So let us start with a very simple problem. So in this problem, you have a calibration curve. So we already have seen what is a calibration curve. So the question is, find the following parameters from the calibration curve given in the figure below. So this is your calibration curve, that is the relation between response and the stimuli. In this case, from the curve itself, it is very clear that the sensor is a temperature sensor, and that is why the x-axis is temperature, the y-axis is response. At this stage, even if you do not know what type of sensor it is, I mean this can be a thermistor, this can be a capacitive temperature sensor, whatever it is, you will be able to calculate sensitivity, range, offset from the given information. So I repeat, in this case you only know the calibration curve associated with the sensor, but you do not know whether it's a thermistor or it's a capacitive temperature sensor or it's a device based temperature sensor. This information is not given over here, but the information given over here is sufficient to calculate these three parameters. Okay, so one may argue that as whether this particular information is sufficient or not for this calculation or for figuring out these parameters. So the answer is the information is sufficient. And apart from that, in the calibration curve, they also have mentioned the relation between input and output. So it's a linear plot where your response R is equal to 0.75 into T plus 2.5. So R is equal to 0.75 T plus 2.5. From the curve itself, it is very clear that the calibration curve is linear. From the equation also, it is very clear that the calibration curve is linear. Why? Because it follows the equation y equal to mx plus c. So this is the generalized equation for a straight line where m is slope and y is the intercept. So this is a equation of a straight line. So you can consider that the response of the sensor is linear in nature. It's not a non-linear response, it's a linear response, perfectly linear response. However, in practice, just to give you an information, you may find that getting a linear response like this is sometimes quite challenging. So what we do in that case is, for example, if you take values at different temperatures, you may find the values are coming like this, which is not exactly linear, but if you fit the curve, we also have seen curve fitting, how it helps. So if you fit these data points in a linear function, you will find that the response is fairly linear. Okay, that discussion we already had. Now in this case, we have to figure out from this information 3 parameters: sensitivity, range, and offset. And there is another question, which is find out the temperature at T equal to 10 degrees centigrade. Now one can find out this temperature just by looking at the plot. So at 10 degrees centigrade, this is your 10 degrees centigrade. The plot says that this is your response. So at 10 degrees centigrade, your response is 10%. Right? From the plot itself, it is very clear. The corresponding value is 10%. The corresponding value to this 10 degrees centigrade is 10%. So your response from the plot, it's 10%. So it's like find the response, not temperature. So it's find the response at T equal to 10 degrees centigrade, right? Even if you don't have this calibration curve, you can figure out the response from the equation also, because you know R is equal to 0.75 T plus 2.5. So at T equal to 10, the response will be 0.75 into 10 plus 2.5 is equal to 7.5 plus 2.5, which is equal to 10. So your response at T equal to 10 degrees centigrade is 10%. So from the equation as well as from the curve, you will be able to figure out what is the response of the sensor at T equal to 10 degrees centigrade. Okay. Now let us see what is the sensitivity of this sensor. Now we know that the sensitivity of a sensor can be calculated from the slope of the calibration curve at that particular point. Now in this case, as your response is linear, the slope of this calibration curve is constant throughout the operating range. And we have seen that the response follows y equal to mx plus c equation, that is an equation of a straight line where m is the slope. And if you compare this with the response equation, your m is equal to 0.5. So in this case, the sensitivity of the sensor is 0.75% per degree centigrade. This is the unit of the sensitivity. So from this equation, you know that your sensitivity is 0.75% per degree centigrade. Just by measuring the slope, you can figure it out, right? So this is what it is given. Once you compare your equation with y equal to mx plus c, you will be able to figure that out. Now the next question was, what is the range of the sensor? Now in this case, if you look at the plot, the temperature sensor is operated in this range, right, between 0 to say 25, 26, 27. So from the plot, you will be able to understand that the operating range of this sensor, at least from this plot, it is understandable that the operating range of this sensor is 0 to 27 degrees centigrade. Until and unless it is explicitly mentioned somewhere that the range of the temperature sensor is something different, you can measure the range from the given calibration curve plot. this is how you can actually decide what is the range of the sensor, until and unless it is explicitly mentioned in the data sheet somewhere. The range can be 0 to 80 degrees centigrade, but one can only give you the plot between 0 to 27 degrees centigrade, because you know the calibration curve follows this equation. So you can figure out the values without the curve also. That is possible, but if it is not given, then from the plot only you will be able to understand what is the range. Okay. And then the third question is, what is the offset associated with the sensor? Now we know offset is the value or the response of a sensor when the stimuli is 0. In this case, the stimuli is temperature. So at t equal to 0, whatever is the response is your offset. So from the plot, if you check the value at t equal to 0, it's somewhere near or between 2 to 3, right? Because this is 1, this is 2, this one is 3. So your intercept is somewhere between 2 to 3. But it's very difficult to figure it out from the curve, because whether it's 2.2 or whether it's 2.3 or 2.5, nobody knows, or it's very difficult to actually gather extract that information from the plot. So what you can do is, if you have the equation with you, you just put t equal to 0 in that equation. So your r will be 0.75 into 0 plus 2.5. So it is giving you 2.5. So in this case, you can very accurately measure what is the offset of the sensor. At t equal to 0, r is equal to 2.5. That means the offset of the sensor is 2.5. And you can also check the same from the plot. If you do not have the equation with you, then you have to guess from the plot if it is not exactly mentioned or properly shown, that is somewhere between 2 to 3. But the accurate value you can get from the calibration equation only. So in this case, if you put t equal to 0, then your r is equal to 0.75 into 0 plus 2.5, which is equal to 2.5. So this is how you can calculate different parameters like sensitivity, range and offset from a given calibration curve or a given calibration equation. Okay. Now let us see another problem where, say you have 3 different temperature sensors. Say this is the first temperature sensor, this is the second temperature sensor, and this is the third temperature sensor. And from the plot itself, it's very clear that all these temperature sensors have different calibration equation as well as calibration curve. So the calibration equation for temperature sensor 1 is given over here. Say this is equation 1. For temperature sensor 2, the equation is, say, equation 2, and for the third one, it's equation 3. Now the question is, which of the following sensors has highest sensitivity? Now we already know that the sensitivity is nothing but the slope associated with the calibration curve at certain temperature value. Now in this case, all 3 are linear responses, right? The first sensor response is also linear, the second sensor response is also linear, the third sensor response is also linear. So the slope for all 3 sensors or all 3 curves are same throughout the range. Throughout the operating range, the slope is constant. So again, if you just compare these equation with y equal to mx plus c, then the value of m for the first sensor is 0.75, for the second sensor is 1.21, for the third sensor is 2.15. So from this only you will be able to understand that the third sensor has highest sensitivity. Even if you don't know the equations exactly, then also you will be able to tell that which sensor has highest sensitivity just by seeing the steepness of the curve, how fast it's changing with respect to input. So if the curve is steeper, so the slope will be higher, so the sensitivity also will be higher, right. So just by looking at the curve also, without doing any calculation, one can say that the third sensor has highest sensitivity because it's steeper than other two alternatives, right. So it's visually also very kind of visible. The next question is, which sensor has highest offset? So again, to check the offset, what you do is you put t equal to 0 in all three equations, and then you will see in the in case of first sensor, the R is equal to 2.5 for t equal to 0. For the second equation, R is equal to 0.7 for t equal to 0. For third equation, R is equal to 0 for t equal to 0. That means the offset is highest for the first sensor. Even if you look at the intercept here, from here also you will be able to understand that at t equal to 0, this sensor shows the highest response. That means that sensor 1 has highest offset. So you don't need to do a separate calculation in order to figure out the offset as well if you have the calibration curve with you. If you want, again, if you want to measure the offset very precisely, it's better you use the equation and put t equal to 0 into it, and then you get the precise value of the offset. Otherwise, visually also you can calculate. To some extent, you will get an idea. Similarly, let us see a response which is non-linear. Say in this case, you have a temperature sensor where the response of the temperature sensor is non-linear and follows this polynomial equation, and the curve looks like this. In this case, if someone wants to know the sensitivity of the sensor, then it is also important that you have the temperature value at t equal to what you need the sensitivity, because the sensitivity is varying. I already have said sensitivity is nothing but the slope of that curve. Now, for a linear equation, it's very easy. You compare it with y equal to mx plus c. But for an equation like this, where r is equal to 4 into 10 to the power minus 4 t cube plus 2 into 10 to the power minus 2 t plus 4.55, for an equation like this, if you want to get the value of slope, what you do? You do the first derivative of that equation, and this will give you the equation for the slope, right. So it's like 3 into 4 into 10 to the power minus 4 t square plus 2 into 10 to the power minus 2. So your slope is also a function of time, function of temperature, that is stimuli. Your slope is also a function of temperature, that is stimuli, right. So in this case, if you change the temperature, your slope also will vary. From the figure also, it's very evident. So the slope here will be different from the slope here, because the tangent, if you draw a tangent at this point, the slope of this tangent is different from the slope of the tangent at this point. So that sensitivity of the sensor is actually changing. However, if you look at the response, say between 52 or say this point to 60 or maybe 65, whatever it is, you can calculate. In this range, if you look at the calibration curve, it's fairly linear, right. So in this case, you may figure out, you may tell that the sensitivity is more or less constant in this range. However, in this range, if you look at this range from 20 to say 40, the slope is actually varying with temperature, right. So this particular calibration curve has a linear response, or you can say fairly linear response in this range, but in the low temperature range, it's not that linear. In the very low temperature, say 0 to this point, it's actually very less sensitive. So this sensor cannot be used for a very low temperature. You can see that the slope here is almost parallel to the x-axis, that means the slope is almost 0. That means sensitivity is more or less 0. So there is no point in using a sensor where the sensitivity is 0, right? And throughout this range, the sensitivity is actually a function of temperature. So if you put different values of temperature, you will get different values of sensitivity. So that is how you can decide the slope at a particular temperature just by putting that value over here. So it doesn't have a constant sensitivity like a linear response. Okay. And then as far as the range is concerned, in this case, the operating range also can be calculated just by looking at the plot, because it's not mentioned anywhere. And if you want to calculate the offset, in this case, again put t equal to 0 in this equation, and you will find that this term will become 0, this term also will become 0. So the offset is 4.55. Now if you go by the calibration plot, you may find that this value is 4.5 or close to 4.5, but the accurate value is 4.55. So it's better if you have an equation, you calculate the offset from that equation rather than considering the visual plot until and unless it's very precisely mentioned in the graph. You can take the help of the equation given. So you just put t equal to 0 and you will be able to get the offset of that sensor. So these are the considerations associated with different calibration curve and different parameters. So with this, we are concluding sensor parameters and some of the calculations I have shown you, which will help you to solve different problems as well, or which probably will help you to understand a calibration curve in a better way. Okay. So in the upcoming discussion, we will discuss different sensor physics. Till then, thank you.